Morning, good afternoon, good evening, everyone. We are starting our first webinar this semester, and this time we have Dana Longcop. Dana Longcop grew up in a suburb of Worcester, Massachusetts. He received his PhD in applied physics in 1993 from Cornell. He was then a postdoc at the Courant Institute of New York University, and then a researcher and a Miller Fellow at Space Science Laboratory at the Department of Astronomy at University of Berkeley. He is now a professor in the physics department of Montana State University in Bozeman, Montana, where he has been since 1996. Over his many years, he has conducted research into magnetic field evolution in the solar corona and the solar convection zone, on magnetic energy storage, and on magnetic reconnection. And today we have a talk about storage, release, and conversion of magnetic energy by solar flare reconnection, a story of large scales. So please go ahead. I will let you know 5 minutes before the end.
5 more minutes before the end. Thank you. Good morning, everyone. I'm going to talk to you about sort of the large story of flares, and this is just to remind us all. I know many of you have seen these talks on flares, and the left here shows some images from AIA that are of the very famous flare, September 10th, 2017. It's a coronal mass ejection. The very leftmost image gives you a nice picture of that sort of flux rope leaving the sun, and the next two are the sort of structure that looks so much like this standard flare model cartoon. Basically, I just want to remind you how, that this cartoon does seem to explain some of the things we see. We've got a big, long current sheet that's left behind by the flux rope, and a little tiny region where we believe reconnection is occurring. Magnetic field is being reconnected by an electric field within some small diffusion region, and from there, we have these jets, outflow jets, with some shocks, some heating in them. I know a lot of people talk a lot about what goes on in this diffusion region, but I'm going to talk exclusively about the jets. I'll try to convince you where all the magnetic energy is being converted into other forms. And really, if you're interested in the energy of a solar flare, that's where you want to look. The flare itself is mostly manifest by the loops underneath these jets. I'm trying to trace with my mouse. I don't know. Is that evident to everyone? There are people who can see the.
Yeah, you can see it, yeah.
Yeah, okay. So these are the loops that we observe. There's some signatures just above the loops and above the loop top source. And then down in the surface, there are these flare ribbons about which I'll talk more. Okay, so that's the sort of the context of the story. And I'm basically going to tell you with that cartoon, mostly in cartoon form, about the storage, the release, and the conversion of energy in that kind of thing. And so here's an even simpler cartoon of this whole thing. This is a model. Many people were looking at models like this, but the most famous version is by Terry Forbes and Jun Lin. And here we have essentially a line current, which is forming a flux rope, going, I guess, straight into the page, maybe coming straight out of the page. And there's a photospheric magnetic field that forms a dipole that goes over this. And the interaction of those two magnetic field systems forms this little X point. But this is not in force balance, and I've shown an energy diagram on the right. So the system right now is at the edge of a potential well, and when I release it, it essentially goes up and then comes back down and settles down into the bottom of that potential well. And the thing to notice about that is that X point gets deformed into a large current sheet. And this is actually the equilibrium state of this magnetic field. I have enforced the condition that no magnetic reconnection is occurring. There's no electric field inside that current sheet. So the flux, this gray region and then the gray region in the flex rope is not changing. So what we get is this distribution of current that I've shown by this loop here. And so that's the bottom of the potential well. You can't actually get an eruption in this simple model. If you try to keep the flex rope going up, the energy just increases, in this case without bound, and this is something known as the Alley-Sturrock conjecture. But what's really happening is that current sheet has the same sense of current as the flex rope itself. If we have sort of current coming out of us in the flux rope, then we also have a positive current in the current sheet, and that is creating an attractive force that's keeping the flux rope down. And essentially, the higher it goes, the more current there is pulling it back down, and it can't get away. So it's that current sheet that's creating this. You can see here the magnetic field in this simple model. If I plot the magnetic field strength on this dashed orange line, it's discontinuous. It's a jump in BZ, and that's what's creating this current sheet. And the X point has basically been deformed into that. So in order to actually get an eruption and to get a flare, what we need to do is allow that some electric field inside this current sheet. So we'll say that the electric field is not zero, and that allows the amount of flux, say, underneath the current sheet, that is this closed flux, to increase over time. That means the current will actually decrease as well, which gives us a smaller downward force, and the flux rope will be able to rise. That is a CME. It is these loops that are being reconnected and moved into this region below the current sheet. That is the solar flare. So in this simple picture, there's a clear distinction between what is a CME and what is a flare. The flare is just this lower region where the magnetic field lines have been closed, are going to have energy flow into the chromosphere, create ribbons, etc. In this cartoon, they're just little orange triangles. But if we watch a movie of this, that's what happens. It really does extend the current sheet and allow the flux rope to escape into space, but only because I have allowed the flux to change underneath this. And the question is, how much energy can we get out of this process? How is that energy, how much energy is being stored and then released? We know it's stored in this current sheet. And to answer that question, or at least give you a really simple version of it, I'm going to actually fix the flux rope, keep it in one place so that there's no work being done on it. The force on the flux rope will change, but there's no velocity, so there's no work being done. And we'll find the total amount of current we have here, that is the area under this current density plot. Integrate that area, that'll tell us the total amount of current. And then if I look at the amount of flux inside this gray region, that's the reconnected flux. Okay. And so when I do this, and I basically allow the electric field to do its thing, the current sheet shrinks, the current goes down, and the flux goes up. Okay, that's a pretty simple cartoon picture of how reconnection is going to decrease the amount of current in my current sheet and increase the amount of flux interconnecting the magnetic sources in the photosphere. Okay, so now we're getting ready to do some physics here. I have a scenario in which the current is changing in time, and here I've shown you a couple of snapshots, and the green line is the current sheet, but I've integrated the current in it and plotted it here in blue against this blue axis, and it's going from whatever its initial value was down to 0 over some time 1. At the same time, the flux, the gray area, is increasing. Okay, so flux is starting at some value and increasing over time. And the important thing is the energy, the work done by the magnetic field. And we want to be very careful what we're talking about here. This is the work that the magnetic field is doing on everything else. And that is just found by time integrating the power, that is the current times the electric field, then using Faraday's law, and that turns into an integral of I d phi. So basically, if I, instead of plotting I and phi as a function of time, I plot I as a function of phi, then I get this blue curve. It starts off at the same place and it falls to 0, and then I get this gray area. That gray area is simply the amount of work done by the magnetic field, the electromagnetic work done by the magnetic field on something. It's the energy released. So that sort of answers the question right there. How much energy is being released in this process? What I need to know is the current in the current sheet and the amount of flux that is reconnected through the current sheet, and then I just construct this kind of integral. Or since I don't really have this kind of data available, I can just approximate this as a triangle. You can see that if I link this as a triangle, I'm going to get a very, very close to the correct answer. And I do know how to find the area in a triangle. By the way, the electric field that is doing this reconnection is essentially the slope in this flux curve. So once I measured phi, I can measure d phi dt. And these are all things we actually can measure, and they're not all that, well, they're difficult to measure, but we can do it. Here is an image of a flare. This is from Boxing Day 2011, and Boxing Day is December 26th, just a clever way of referring to that date. On the left, I'm showing you the 1600 angstrom image from movie from AIA, and on the right, 171 angstrom, which is going to show us some of the flare loops. But the important thing is we see these flare ribbons. We see the brightening that's caused by the reconnection, and it moves outward, just like in that cartoon. Essentially, the magnetic flux is being reconnected, and I'm seeing the impact on the chromosphere of that energy release. Then we see these nice little loops, and you're looking more or less down on this whole process. So these loops are, you're looking straight down on them. They show up a little bit later because we do have to wait for the plasma to cool into that bandpass. I'm not going to worry at all about that, except to show that yes, this is very consistent with a cartoon. There's our cartoon. The loops are these blue lines inside the gray box, and the important thing is the flare ribbon, which is the shown in 1600, is basically showing me as I track it how much flux, what this orange ribbon rectangle is. And this is some nice work that Zhang Chu has been doing and continues to do. And here we see her mapping the location of the flare ribbons at different times. And the color bar, if you can read it, is in minutes: 15, 25, 35, 45, 55 minutes, going from dark blue, violet up to red. And you can see that they indeed progress outward from outward away from the polarity inversion line. More importantly, we can basically add up all the magnetic flux, B dot D area, that they're covering up, and give us a plot of the flux that this is reconnecting. And it is very two-dimensional, except it is only a finite length long. So it's about 75 megameters if I want to give myself a third direction in this essentially two-dimensional cartoon. But so in the red here, this is her plot. She's shown the amount of magnetic flux covered up, and their thickness here indicates the level of uncertainty. And the uncertainty, first of all, comes, you can kind of get an idea of the uncertainty because you've got two versions of this, the positive and the negative. So that's one way of establishing how much uncertainty, but it clearly starts out at 0 and goes up. This is very similar, although it's not going up linearly, it's going up a sort of fast and then slowing down. But this tells us how much flux has been reconnected. And let's just start at that right now. So we know delta phi, we know the amount of flux that has been transferred through this ribbon or through this current sheet. And from the amount of flux, and so essentially that's the amount of flux that is going to this is going to change when I take the current to 0. If I say the current was at some initial value and then goes to 0, then that amount of current really is, and this is just an application of essentially Ampere's law. The amount of current initially in that current sheet is this flux divided by our good old mu naught times the length. That's it. So this tells me that we had about 160 gigaamps of current in that current sheet before this flare occurred. And by the time that was ramped down to 0 and the reconnected flux had ramped up to this value, we're getting our energy. And so let's just go over to here and figure out, well, I'm supposed to do the integral of I d phi, and I told you I could integrate the area of a triangle. It's 1/2 the height times the width. And so that is I naught phi, and we get the energy that has to have been released by this flare on December 26th. Just from that simple measurement, we have a very good idea of where that energy, how much energy was released from the magnetic field. As a side note, we can take a derivative. We do have some errors on this, so the error in the derivative is going to be very big. But if you remember, d phi dt is related to the electric field, and actually it's the electric field times that length L. So that gives me about 10 to the 10, basically 10 gigavolts is what the loop voltage through that current sheet is at the peak. And you can see it drops down to 0, but not immediately. It does take the better part of an hour to fall off from its peak value down to something like 0. So this is reconnection that's progressing over time, but that's what's required to transfer all of this flux. So this is a version in which we have a flex rope that's creating this current sheet, and there is the magnetic field is doing work. It's decreasing in energy. Some of that energy may be going into accelerating the flex rope, and others to the flare. I want to just do a quick version of a different scenario for the storage and energy release, which is actually going to have all the same properties in the end, but it has some different aspects that I think are worth noting. And this is a different flare, February 20, it actually starts on the 24th, and it's going to go for a couple of days. This is an MDI magnetogram of just this active region. So you see it's a bipolar active region. We have a big positive region on the right and a negative region on the left. And then over time, there's some flux emergence. You see some new positives and some new negatives appearing. And they just push themselves right into the region along with the existing positive and negative polarity. So this is flux emergence and a picture, a two-dimensional picture of how this would store energy. Goes back to Havart's Priest and Rust way back into the 70s. And here again, we have a nice cartoon with the same color scheme I was using before. We have blue field lines. I have basically an overlying field, even though they're not really overlying. We'll get to that. But basically positive P1 connecting to N1. And then the new flux is this P2N2 region that gets pushed up underneath the existing flux. And following the same scenario we had in the flex rope case, I'm going to imagine that process occurs. The flux between P2 and N2 increases, but the flux connecting P1 to N2, which started out at some value, because I didn't start with this, I didn't start with 0 flux in the new region, but it has some value, but I'm not going to allow that value to change. So as the flux emergence occurs, I have to establish this current sheet, which separates the old overlying field lines going left to right, here shown in orange, with the new ones in green going right to left. And that's the equilibrium current sheet that would be analogous to the one underneath the flux rope. That is the way this scenario works. The current sheet is, again, the lowest energy state I can get to without invoking reconnection. If I do reconnect, I will shrink again that current sheet down to from its initial current to zero current, and I will transfer flux from P P2 N2, the new flux. I'm going to increase the amount of flux connecting to the old flux. So you'll see that these orange line in the lower end goes from, well, it goes orange and then green. It's basically connecting P1 to N2. That's the total amount of flux that I've transferred. So while the scenario for creating the current sheet is different here, there's no flux rope, possibly no coronal mass ejection, and quite remarkably, this flare here, which was an X flare in 2004, was an X flare and there was no coronal mass ejection associated with it. We believe it was just due to this emergence and a current sheet built up, and then magnetic energy was released all at once or over a course of an hour or so through reconnection. But the amount of energy released is exactly the same formula. It's basically I times delta phi. So the big problem is this is not the two-dimensional picture that Priest, Havarts, and Rust were envisioning. Instead, we have an old active region that's basically going from right to left and a new active region that's going from right to left. They're more or less parallel, but they do encounter each other. And if you trace this all out in 3D, and there's a lot of interesting talks one could give about the topology of three-dimensional magnetic fields, I'm going to just cut to the chase and say we have some different numbering here, but the old flux is essentially going from P4 over to, I think I call it N1, and then there's a P9 to N5. That's the new emerging flux. That's the newly emerging flux. And over here, in the inset, I have a key, the old regions and the new regions. And there's a region, a line, a magnetic field line, and it is a magnetic field line. It's not a null, along which those two regions have to develop a current sheet. And there's a picture of the current sheet in green, and you can do the same ribbon tracing and find out that there was a certain amount of flux built up, 3 times 10 to the 21, or released, transferred during the reconnection, 3 times 10 to the 21 Maxwells. You can do the same trick. I have this magenta line is 50 megameters long. I can estimate the current by dividing the flux by the length. And instead of this time, I think I get 400 gigaamps instead of 160 gigaamps. It's all pretty similar numbers. And from that, you can figure out the total amount of magnetic energy stored up or transferred. Sorry, this is the amount of energy that was released during the flare. And that's all based on these kinds of estimates. So I've just given you two versions of how these flares can store and release energy. In every case, they're developing current sheets because that's the lowest energy they can get to without reconnection. And it seems like the reconnection waits a while to occur. In this flare, you saw that emergence was going on for 2 days before the flare actually happens. And then the flare is basically transferring, and that's what reconnection really is, the flux through the current sheet. So this is where we get to sort of sit back and say, okay, so we know how in these two scenarios to calculate the work done by the magnetic field, by the electromagnetic field, and it's just the area in this I phi box. It's just ID phi. And that looks very familiar. That comes from integrating the current times the electric field. And we see that in contexts of, say, solid resistive materials, and we associate it with ohmic or joule dissipation. In this case, we actually have a plasma, and so although that is the work done by the magnetic field, it's not joule dissipation. That formula just tells you the magnetic energy goes down. It does not tell you what happens to that magnetic energy. This is a very important point, and I just stress it because a lot of times people just see that formula and assume, oh, that's resistivity dissipating energy, and it's not. We're going to go into what actually happens to it. Mostly it turns into kinetic energy moving this plasma around. But That's just a spoiler. We're going to ask the question, what happens to it? Where does it go? And how is it converted maybe into other forms that are even more commonly associated with flares? One thing I want to point out using this simple Priest-Havarts and Rust cartoon is in the middle panel, I have that magnetic field with a current sheet. That's the initial magnetic field. In the bottom panel, I have a potential magnetic field with the exact same boundary conditions. If I subtract those two, I get the magnetic field due only to the current, okay? And the current is responsible for storing the free energy. That is the total amount of energy above the potential field. And that is just found by integrating the magnetic field you see in the top. And quite notably, the current sheet is this thin little red line, and these contours go everywhere else, right? There is a great volume holding this magnetic energy. The magnetic energy is not present in the current sheet itself, even though the current sheet is a manifestation of the energy storage. It's not where the energy is stored. Okay, but we still need to sort of figure out what's going to happen when I release that. And for this, I'm going to go back to this integral of I d phi, and I'm going to ask, that's the work done by the magnetic field when it transfers all of the flux. I'm going to say, what's the work it does if it just transfers some infinitesimal element, delta phi? So we just imagine a small piece of flux is reconnected, and I want to know how much energy does that release? And it's easy. It's just, one element in that integral. It's I over c times delta phi. And if I use Ampere's law, I can write the current I over c using this integral along a path P. And on the left, I've shown you the traditional view of a current sheet. So it's a slightly different current sheet than we've seen before, but you get the picture. Magnetic field is going up on the right, coming down on the left. That's creating this current that's going straight at us along this line. And essentially by creating an Amperian loop that surrounds that and integrating B dot dl along that Amperian loop, I'm getting the current. And that's going to tell me the total amount of energy that can be released. This is the edge-on view. This is the view everyone likes to have of a current sheet. I want you to imagine there's also a component of this magnetic field that's into the page. Okay, so the magnetic field on the left is actually going down, but it's actually going down and into the page. The magnetic field on the right is going up and coming out of the page, or going into the page as well. If we turn 90 degrees, or if we look from, let's say we're going to look from the right, then that's the inset picture here. Those field lines, those blue field lines, are no longer just going up. You'll see they're going up and to the right. They're going up and to the right. The red field lines are going down and to the right. The guide field is to the right. The current is now flowing to the left in this view. So this is an orthogonal view of the same current sheet. And what I'm going to do is I'm going to take my loop, which has to enclose that. It just has to be an Amperian loop. It just has to enclose the current. And I'm going to make it follow the field lines. So the upward path is going to go up and to the right. That's P1. And then to go over the top of the current sheet, I'm actually going to follow the horizontal top of the current sheet and go to the left. And then P3 will be going down and to the right and then back around. So it has this cool little figure 8 pattern. It follows the magnetic field lines. So B dot dl is basically B along the magnetic field lines. But otherwise, it's giving me the exact same answer. Then I'm going to do one other thing, right? I just have to do this integral along this figure 8 type path. And that's going to give me the energy. I'm going to separate two of the legs, the magenta and the maroon legs here, and call those P1 and P3. I'm going to include those in one integral. And then I'm going to take the other two and put them in a second integral. And I can take my path and, add it in any way I want. So all I've done is just applied Ampere's law and, chosen my Amperian loop in a very suggestive way. Nothing that we don't do in sort of freshman or sophomore or junior level physics, except this is kind of a complicated current system. Now I'm going to do something that seems kind of weird. I'm going to take those those P1 and P3 legs, and I just have to integrate along them and add up the integral. So I can break them again, and I'm actually going to create one that consists of part of P3 and part of P1. I'm going to call that PI, and it goes up to a point where they cross and then back down again. And then PI prime will go down to the point where they cross and back up again. I've just taken two legs and rearranged the sum so that they're like that. The second thing I'm going to do is I'm going to take the horizontal legs, and I'm just going to do the integral from left to right and change the sign in my sum. Okay, so it's going to actually go against, now it's going to go with the magnetic field, but all I'm doing is changing the direction of those integrals. And so the sum before is now a difference, and it's PI plus PI prime minus PF minus PF prime. But by doing this, what I've done is, if there were reconnection occurring at that yellow dot, then PI and PI prime would be the magnetic field lines that result from that reconnection, right? All I've done is broken the magnetic field and reattached it that way. And there's some tiny little region where things have changed, and so my integral has, I'm making maybe a tiny little error there, but you know, we're interested in big amounts of energy, so I'm not going to worry about that too much. So those are the magnetic field lines after the reconnection, totally after the reconnection has stopped, but before any retraction has happened, before the magnetic flux has actually been moved out of the current sheet. And the Fs are the same magnetic field lines, but after they have been moved by the outflow, the reconnection outflow, to the edge of the current sheet. Okay, so this is conceptually a big jump, but it's the same integral. So now what the integral is telling me is that first integral over PI and PI prime is the energy per differential amount of flux in that occurs before the retraction. It's after reconnection, after the actual reconnection, but before the retraction. And then the other integral is the energy after the retraction. So the energy released is just the difference of before minus after, which really tells us the story we really need to know, that somehow when we undergo reconnection, the way we're actually getting energy out of it is by decreasing this integral B dot dl along those field lines. And it's worth now going back to the old Havarts and Priest kind of field and looking to see, well, why does that integral decrease? Because of reconnection. And here I've traced out one field line, and it's the exact same, basically the flux is leaving from the exact same place in the before and the after. This is before any reconnection has occurred. And I'm basically going, there's symmetry, so I'm only calculating the integral of B dot dl along here, along the magenta line, and then along the green line. On the bottom, I have plotted what B is as a function of loop length, arc length along this line. And just to make things a little confusing, because the magnetic field is very big right at the feet, I've put the feet together on this graph. So the length position at each foot point is 0, and in the magenta line, length goes from 0 to a negative number, and in the green line, it goes from 0 to a positive number. And so basically, the green field line is to the right of the feet, and the magenta field line is to the left. I'm sorry, that is a little confusing, but it really helps us visualize what's going on. The top of the magenta field line is this point over on the left. And the before, I should say, is actually the dashed line with the gray area under it. That's the integral of B dot dl before the reconnection happens. The integral of B dot dl after the reconnection happens, and you can see it's a very different looking field line, but the dashed magenta and the solid magenta are almost on top of each other. The magnetic energy of that part of the loop has really not changed at all. And the magnetic energy of the other portion has changed, but B has really not changed that much. What really matters is the field line has gotten shorter. The whole change is really due to a magnetic field that doesn't change very much in strength, but the magnetic field line gets shorter. And after all, the integral of B dot dl, you can imagine that as either taking a fixed amount of length and integrating how much magnetic field strength there is, so maybe the magnetic field gets weaker, or a pretty uniform magnetic field strength and the field line gets shorter, right? Either one can happen. It turns out in most of these cases, when you look at it, only the latter happens. The magnetic field, magnetic reconnection, and this again is a very, I'd say, counterintuitive or misunderstood aspect of magnetic reconnection. It's not weakening the field per se, it's just making all the field lines shorter. And that's where our energy comes from. And really interesting, if you think about it, is the volume. The total volume is found from a different integral, and that's dl over b. And well, basically, since b hasn't changed, it doesn't matter whether I divide by a constant or multiply by a constant. The volume is decreasing because the lengths of these field lines are decreasing. That means the plasma has to get compressed. So not only does the magnetic energy go down, but the volume goes down, and the plasma has to be compressed. So here's a sort of even simpler version that's just reiterating the same point. If I think of the magnetic field as the energy as the integral of BDL, then the picture on the left has two field lines. Again, they're green and magenta. In this case, they haven't reconnected, and they are the shortest field lines they can be given their foot points, right? They're straight. They cross at a point. Now we have this mysterious diffusion region, a little ball where I'm going to change the topology of these field lines. Now that will decrease the energy. I'm not denying that that happens. But since W is very, very small, it's a small change. So the actual reconnection due to the electric field decreases the magnetic field a little tiny bit. What really makes this magnetic field have less energy is when the top field line straightens out into a magenta green field line and the bottom one straightens out into a green magenta field line. And that basically requires the outflows away from the reconnection point. Okay, so the dissipation, the ohmic dissipation in this case, or whatever the dissipation mechanism is, and people argue about it all the time, I think it's an interesting argument. It's energetically negligible, right? There's no point in which their argument about what goes on in the diffusion region will help us understand the energy released by flares. It's happening on too small a scale. The energy release does not involve a non-ideal electric field. It just involves these reconnection outflows. That's where the energy release is coming from. And I promised to talk a bit about how that conversion is happening. And that is something I can't say I know the whole answer to. But there was an answer that really was provided, and it may seem like it was doing a different job at the time, but this really is the answer we're looking for. And it's the Petchek model. So Petchek does explain this. That doesn't mean I'm saying Petchek happens. I'm just saying here's an explanation for what could happen to the energy. And the bottom left picture is a sort of classic picture of Petchek. We have a diffusion region in this little red circle. I have a magnetic field that's mostly up and on the right and down on the left. This is 2.5D Petchek, so there is a guide field, BZ coming straight at us. So if I look at the top, that's again a picture of field lines that are going up and to the right and down and to the right, and they are misaligned by an angle delta theta. Delta theta is the view I get from the face-on view of the current sheet. It has nothing to do with the wedge that you see in the bottom left. That angle of that wedge, again, is a topic of much discussion, but it's irrelevant for what we're talking about here. And because this is 2.5D, there's actually two shocks that occur in this reconnection scenario. One is a rotational discontinuity. The magnetic field strength does not change, the temperature does not change, the density doesn't change. Only the direction of the magnetic field changes, and the kinetic energy does, or that there is some change in the kinetic energy, right? And then on the inside is what are known as slow shocks. So this is the classic picture of PetCheck 2.5D PetCheck reconnection worked out by these authors along with many others. If we just focus, I want to focus on one of these field lines, one of the field lines that goes up and to the right and down and to the left, making an angle delta theta. And so here's the angle delta theta, and after it's partially retracted, it's making this angle delta theta over 2. Okay, and if you just look at that one field line, you see the rotational discontinuity. It's basically the bend in the magnetic field.
Dana?
Yeah.
You have 5 more minutes and something wrong with the sound.
Oh, no.
Maybe just not too close to the microphone, so just maybe you can check how.
Step back or go forward? You can't hear me, or you can...
Yeah, now it's fine, I think.
Okay. Okay, yeah, so we're almost done here. Good, 5 minutes will be perfect. And so what happens at this rotational discontinuity is we get velocity, it goes downward and to the right, basically. That is due to the tension at this bend in the magnetic field line. And as I said, a rotational discontinuity, the magnetic field strength hasn't changed, the density hasn't changed, the temperature hasn't changed. But what has changed is we get this velocity here. And some component of that velocity is parallel to the magnetic field line. Actually it's sending plasma rightward. On the other side, it's sending plasma leftward, and those two streams of plasma will collide, and that's what creates the slow magnetosonic shocks. If we think about it just as a tube, those slow magnetosonic shocks are really what you get in a shock tube. Those are gas dynamic shocks. And that is where the component of the magnetic energy, the kinetic energy, is thermalized. Well, as long as you have collisions. If you don't have collisions, you just have two counterstreaming plasmas with very small temperatures, but the temperature of the combination is exactly what the shock conditions would tell you it would be. So whether you believe there are shocks or not, you know that this density this plasma has a higher density and a higher temperature, and it has reduced its kinetic energy because it's no longer flowing left or right; it's just going straight down. So that gives us some handle on how much of that kinetic energy is thermalized. Basically, in another cartoony picture, we have a velocity that's related to the angle of the magnetic field and the magnetic energy density. And at the rotational discontinuity, that's purely kinetic energy. There's no heating has gone on. And then at the shock, there's some amount of thermalization. So you can work out exactly what fraction, and the fraction is the ratio of the red area to the green area, and that's basically going to go as it's going to go as a square of that that shear angle. So this just gives you an idea that at least in one scenario, we have a way of figuring out how much energy goes into what. Here's a picture that goes back to that first geometry I showed you. We have sort of field lines going up and to the right, field lines coming down and to the left. And here's when you solve the actual fluid equations inside them, you get the downflow, you get the rightward and leftward parallel flows, you have a jump in temperature, etc. And the last thing I'd say is when you can take that kind of picture and go all the way back to that February 26th flare, what you see is if you use this picture, which is a fully developed picture of how energy is converted from magnetic to kinetic to heat, and then if you include radiation, it's radiated away, then the plasma will get heated up, and here we sort of have the emission in various GOES bands, and then it cools down. The only reason we have such a long-lasting flare is that we're transferring flux in lots and lots of little different elements, and those are the loops that we see in 171. We really see that the field has been reconnected in these little bundles. And so we have to remember there's two electric fields we could be thinking of. A lot of people focus on the electric field that's inside that diffusion region. And that is probably very, very large, and it's creating these little tubes that we then later see as loops. That is not what we're measuring when we measure the electric field. That 10 gigavolts that we looked at was actually telling us, right, each loop is only bright for 2 to 10 minutes, but the flare goes on for 45 minutes. And the reason the flare goes on for 45 minutes is we're constantly adding more flux underneath the current, current, and that's creating the whole flare. So the mean rate is really having to do with how fast we can create new loops. And so we have to be careful. That's the magnetic electric field we're measuring, and it's not related to the reconnection rate that, say, Petschek was talking about in his simple models, but it is what we observe. So I'll just end with sort of the take-home picture, and that's a take-home message, which is the big picture of the flare, that the energy is stored by a current sheet, but it's not stored at the current sheet, right? The current sheet is a manifestation of energy in the corona, but that energy is everywhere around the current sheet. And the magnetic reconnection can release that by changing the topology of field lines across the current sheet. Something has to make those magnetic field lines change from a situation where they are about as short as they're going to get to suddenly having a different foot point and thinking, oh, I could get a lot shorter. And that's what really causes the release of magnetic energy. The retraction of those field lines makes them shorter and therefore lowers their energy. And that occurs after the reconnection, not as part of the reconnection. So it's the decreasing magnetic field lines that are causing that. The decreasing magnetic field lines must compress the plasma. And that is a very different topic. Namely, when we see a flare, we really are seeing hot plasma, but we're also seeing dense plasma. And heating plasma is not so difficult. We can think of a lot of ways of doing it. Significantly compressing it is a much bigger challenge. One of the ways that's classically done to compress a plasma is through shock. And that's really why Petschek gives us the most complete end-to-end picture of this, because it shows you how both the plasma is heated and compressed. And so I'll leave it there as my summary of how the magnetic energy is released in a flare. Thank you.
Thanks, Dana, for the very nice summary of the flare. Now we're open to questions, so you can unmute your microphone. I'm looking for the list. And ask question. Yeah, Hugh?
Okay, may I go first? Hello?
Yeah, go ahead.
So Dana, could you elaborate a little bit further on the gigavolts electric field? Of course, if you have that kind of strong electric field, you'll accelerate particles. And so where does that fit into the general picture?
The gigavolt field is just taking the d phi dt, and it doesn't tell me where that electric field is or that it's parallel to a magnetic field, right? All I'm doing is taking flux that I haven't measured, Zhang Chu has measured, and taking the derivative of that flux. I don't know any more than you do where that loop voltage is occurring, but it must be there.
Right, so you're saying you don't know the answer to the question.
That's exactly what I'm saying.
I think it's really important because we see these particles, we see non-thermal particles, and we need an electric field. Or that's one good way to get them. So I got to solve this problem.
You certainly don't see any 10 gigavolt electrons. So I don't know. One answer is to say, oh well, that's a voltage that is taken up in a bunch of series resistors, if you want to think in circuit terms, and no resistor has 10 gigavolts across it, and maybe the particle acceleration is playing the role of the resistor, and you must be doing this in series rather than in parallel. But that's just, pointing out that just because you have a big voltage doesn't mean that every single resistor has that big voltage across it.
Right.
But I have yet to work out where that electric field would be. But I'm just going to say we do know that that voltage is there, that flux change is there.
Okay. Other questions? Bin?
Yeah, I have a
Yes.
quick question. This is a very nice talk and understood a lot. So if you reduce the angle for your scenario,
Right.
that basically reduce to the standard paycheck without any guide field. So my understanding is the shortening.
Can I just correct you? Not if you decrease, if you increase. The reconnection in 2D pet check is basically a reconnection angle of 180 degrees.
Ah, I see.
The magnetic
Okay.
fields are opposite each other.
All right. So, okay, so that will give you the most shortening, right?
That's correct. In fact, if you don't include the legs below the current sheet, in that scenario it's a rather singular scenario because the magnetic field line can shrink to a point.
Right.
And that leads to that's why you really, in that scenario only, do you need to worry about that the opening angle of the in the edge-on view. You can't allow it to be a line. It has to be a wedge.
Mm-hmm.
And it becomes much more difficult. And all I can say is, you're encountering difficulties that you created for yourself. By taking that to 180 degrees, you've really approached the singular limit to the problem. If you give it any other angle that's less than 180, you don't have these problems. Your field line will shorten by a fraction, but not 100%.
Okay, so I saw your formula that the energy
Right.
conversion is proportional to tangent of that angle square. Does this mean if there's close to no guide field, then the energy conversion to thermal plasma would be the most efficient?
Yes. In fact, if you just plug in the, it's actually the angle divided by 4. So 180 divided by 4 is 45. Tangent of 45 is 1, if I'm remembering my trig. So that's 100% conversion.
Okay.
Pretty much in that formula. And that's because I haven't taken into account some of the aspects you really have to when you're trying to shorten something to a point, to zero volume. Yeah. So you have to probably use that formula in the regime where delta theta is less than 180 degrees. It doesn't have to be. It gives you about the right answer when delta theta is up to 120 or even 150. It's not bad. 180 is bad to use it. It's really you're breaking the model.
All right. Thanks.
Yeah.
Okay. Other question, Dale?
Yeah. So Dana, I was interested in your comment that the magnetic field does not really change strength. It's just the length of the field lines that's changing.
Right.
I don't know if you're aware of our EOPSA results where we're actually measuring the magnetic field directly in the volume.
I am aware of those results, yes.
Yeah.
I saw some of them at SPD.
Yeah. So one of the things that we see is, in fact, that the magnetic field does decrease by a factor of a few. But I guess that doesn't really violate what you're saying, because you're just saying that the magnetic field does not need to change. But
maybe
it can change.
been so so forceful about it. There are scenarios where you can get out the energy without decreasing the magnetic field strength. What's really important is you have to decrease the integral BDL. And so if B does decrease, you will get energy out. But also if L decreases, you'll get energy out. And maybe you could have both of them decrease.
Yep. Thanks.
Other questions? Or comments?
Seems to be a pretty advanced class here. The students.
Yeah, maybe I can make. Hugh, you have another question? Yeah.
I think in general, Dana and I could talk for 24 hours about these things because we love this stuff so much. But I could introduce a small disturbance and ask him what he thinks about it, and that is the question about the nature of the current that gets turned off. We think that the energy storage in the coronal magnetic field is because currents link the photosphere to the corona. You know, these have an inductive storage of energy. At least I think that.
Yeah. Yeah.
So, and that current is obviously not being turned off, even if it gets formed into a current sheet. So the question is, how does that energy storage current relate to the current that you see in the current sheet?
Yeah, I mean, that's a really interesting question, and I've tried to explore it in a very different set of models that would be an entirely different talk. If you look at just the current sheet, an ideal current sheet, and imagine turning on a resistivity, so you can do some of that. What you actually see is that current cannot, like you said, disappear, and so it moves with the rotational discontinuities, with the bends in the magnetic field, and that is actually carried outward in this other picture by fast magnetosonic waves. But the current is basically propagated as a wave. It has to move away from the reconnection region. It can't just be dissipated for exactly that reason. So those rotational discontinuities are responsible for carrying that current away. When they get to the bottom of the current sheet, presumably they have to, continue carrying that current down to some lower region where it can find another path. But at no point is the current dissipated. That's actually, like you said, completely impossible. All you can do is move current paths around.
That's really converging with the Melrose picture, because if you move the current around physically, you're changing the inductance, the self-inductance, and so that's where the energy actually comes from.
That is correct. Yes.
Excellent.
John Melrose knows quite a bit.
Again, I meant to come back to Dale's comment and just meant to tell that even so the model and consideration presented are very nice and consistent, does not explicitly include two important ingredients like turbulence and non-thermal particles. So, and these components can change some aspects of the picture. In particular, this change of magnetic field strength can be related to this two additional ingredients. That's just my opinion about it.
I fully agree, and I think turbulence is obviously the first thing that you could imagine adding to this. In more familiar fluid settings like the air, if I try to move stuff around, I encounter turbulent drag. My forces on whatever I'm moving are being countered by a turbulent drag. Somehow that, we have to figure out how that plays into this. The reason I rely on Petschek is no one has really worked out where, how it is that this scenario of creating shorter field lines turns into turbulence, and how much turbulent energy there is. Right? I don't have a formula similar to the one I showed you for thermalization for turbulence, and I'm unaware of anyone who does. If you know of one, please let me know. I'd love to know how we can figure out what fraction of our reconnection energy goes into turbulent motion.
Yes, that's exactly the case. So it's a highly complicated physical question.
I'm not sure it's highly complicated. I just know it hasn't been done.
Yeah.
just because something hasn't been done doesn't mean it's complicated. It means
Maybe. Yeah.
done. But it, I can't see how to do it. And again, that does not mean it's complicated. That just means I'm not thinking about it right. It may turn out to be complicated. It may turn out to be very simple. We can easily calculate the energy lost from our cars driving down the road to turbulence. That's not complicated. We teach that in freshman physics. So if you think about the problem right, you might be able to get the answer, but I haven't figured it out. And then I would argue that would be your first step to trying to account for non-thermal particles.
Okay, so our time is over. So thank you very much for joining. Thank you very much, Dana, for speaking today. In 4 weeks, next one.
Okay.
By Lucia Klein. Yeah.
Thank you.
Thank you. Bye.
Bye.
Thank you. Bye bye.
Thank you.
Who's clapping?